When you look in the mirror, you see yourself. Simple, right? But what if I told you that what you're actually seeing is this incredible piece of physics hiding in plain sight? That's what we're going to do today. We are going to decode that reflection and pull back the curtain on the science that's been in your bathroom mirror this entire time. And we're going to start by tackling a question that I bet you've wondered about, probably while staring into your cereal bowl. Why does your reflection in a spoon flip upside down? I mean, it totally feels like some kind of magic trick, but I promise you it's not. The answer is just pure, elegant physics.
All right, but look, before we can even get to the curve of a spoon, we've got to start with something flat. Your everyday run-of-the-mill mirror. Because if we can master the basics of that reflection you see every morning, that's the key to unlocking this whole puzzle.
So really, what even is a mirror? What makes it work? Well, it's basically any surface that's so incredibly smooth that it doesn't just scatter light all over the place. Instead, it bounces it back in this really organized, predictable way. And that super organized bounce is what gives us the clear, crisp image we see. Okay, let's really break down that reflection you're so used to. First off, physicists call it virtual. All that means is that it looks like it's behind the mirror, right? But you can't actually go back there and touch it. It's also erect, which is just a fancy way of saying it's upright. And of course, it's the same size as you. But here's the cool part. It's laterally inverted. That's the reason why when you raise your right hand, your reflection raises its left. It's that classic mirror world switcheroo. All right, here's a fun one for you. A little mind-bending fact that is just pure physics. If you want to see your entire body in a mirror, from your head all the way down to your toes, you'd think the mirror has to be as tall as you are, right? Nope. Because of how those angles of reflection work, the mirror only needs to be half your height. Isn't that wild? Okay, so we've got a good handle on flat surfaces. Now, let's bend the rules. Literally. Let's bend the mirror, because adding a curve, well, that's where all the really interesting stuff starts to happen. And it's the absolute key to solving our spoon mystery. So these curved or spherical mirrors basically come in two main flavors. You've got your concave mirror, which curves inward. An easy way to remember it is like a cave. Its job is to focus or converge light to a single point. Then you've got the convex mirror. It bulges outward, and it does the exact opposite. It spreads or diverges the light ray. The cool thing is, you don't need some fancy physics lab to see both of these in action. Nope. In fact, I'm willing to bet you have the perfect example sitting in your kitchen drawer right this very second. Yeah, a simple spoon is a perfect little physics lab. Go ahead, grab one. Look into the inner side. That's your concave mirror. When you bring it up close, your eye looks huge, right? But now, slowly pull it away. Just watch. Poof! It flips upside down. Crazy. Okay, now turn it over to the back, the convex side. See? Your reflection is always upright, but it's smaller, and you can see way more of the room around you. It's like two sides, two totally different worlds. So, how in the world can we predict what an image is going to look like without even having the mirror in front of us? Well, physics has a tool for that. It gives us a way to map it all out. Just think of it like a blueprint for light, and it's called a ray diagram. Now, to draw one of these diagrams, we just need to know a few key landmarks. The first one is called the pole, and we label it with a P. It's super simple. Just think of it as the dead center of the mirror's surface. Okay, next up is the center of curvature, or C. So, since these mirrors are basically slices of a bigger sphere, C is just the center of that whole imaginary ball. It's the point that really defines the mirror's curve. And now for maybe the most important point of all, the principal focus, or just F. For a concave mirror, the one that curves in, this is kind of the magic spot. It's the one point where all the parallel light rays come together and meet after they bounce off the mirror. So to map out any reflection, you only need to know 3 simple rules. Think of them like the rules of the road for light. Rule 1, a ray of light that comes in parallel to the center line, it always bounces out through the focus point, F. Rule 2, and what if a ray comes in through the focus first? You guessed it, it bounces out parallel. They're perfect opposites. And rule 3, any ray that passes through that center of curvature, C, just hits the mirror and bounces straight back along the same path. Now here's the cool part. The exact spot where any 2 of these reflected rays cross, bam, that is where your image is going to show up. Okay, drawing these diagrams is great for getting a visual, but if we want perfect precision, we need to speak the language of physics, and that language is math. Turns out there's a kind of secret code, this really elegant formula that can tell us everything the drawing can, and then some. This right here is the mirror formula, and it is incredibly powerful. It connects three key pieces of information. U, which is how far the object is from the mirror, V, which is how far the image is from the mirror, and F, which is the focal length of that specific mirror. It's just this perfect relationship. If you know any two of those, you can always use this little formula to find the third. But what about the size? Is the image bigger or smaller? Well, there's a formula for that too. The magnification formula tells us exactly that. But check out that little minus sign in there. That is a secret clue. Because if your final answer for M ends up being a negative number, that tells you instantly that the image is flipped upside down. Now, to make all this math work perfectly, physicists came up with a really clever system. It's called a sign convention. And really, it's just a set of rules that tells you when to use a positive or a negative sign for different distances. You can almost think of it like a GPS for light rays. It tells the formula whether something is in front of the mirror or behind it, if it's upright or upside down. It's the secret key that makes sure the math gives us the right answer every single time.
Okay, enough with the theory. Let's pull this out of the textbook and look at the real world. Because this stuff isn't just on a diagram. The unique properties of these curved mirrors are being used all around us, and sometimes in ways you really might not expect.
Let's start with concave mirrors. They are absolute masters at focusing light. I mean, that's why they're in your car's headlights. They take the light from a tiny bulb and shoot it out as a powerful straight beam. Your dentist uses a little one to get a super magnified view of your teeth. And on a huge scale, solar furnaces use giant ones to concentrate all the sun's energy onto one tiny spot to create incredible heat.
And convex mirrors, well, they do the exact opposite. They spread things out. This makes them perfect for the side view mirrors on your car. You know, the ones that say, objects in mirror are closer than they appear? They shrink the image down, sure, but in return they give you a much wider field of view, which helps you see what's lurking in your blind spot. You also see them all the time as security mirrors in shops and at blind corners.
And that brings us full circle, right back to our spoon. So, the big reveal. The reason your reflection flips upside down is because the inside of the spoon is a concave mirror. When you hold it far enough away, once you move past its focal point, the light rays that bounce off it actually cross over in the air in front of the spoon. This creates what physicists call a real image. And guess what? A real image is always inverted. So that upside-down version of you, it's literally floating in the air between your face and the spoon.
So you see, the physics of reflection isn't locked away in some lab. It's in your car, it's in your bathroom, it's right there in your kitchen drawer. And now you have the tools to decode it. You know the secret language. So the only question I have for you is, where else are you going to spot physics hiding in plain sight?